Welcome to this biochemistry video on enzyme kinetics. So, as an important note, as a reminder, enzymes are catalysts that increase the reaction rate without being used up. So I just like to think of them as Pac-Man. They just sit there and do their little thing and chomp or eat or add or transform. So their job is to increase the reaction rate. And how they do that is by decreasing the activation energy, which in this chart is delta G dagger. And it's very specific with one reactant, and that reactant is often called a substrate to produce products, and it's very easily regulated, and generally we regulate from low activity to high activity and then vice versa. And kinetics is the study at which the compounds react, and so it's very much a velocity measurement. It's the rate of enzymatic reaction. And that can be affected by multiple factors, including the enzyme, the substrate, temperatures, if there's effectors in the system, all those kind of things. And we'll talk about each one of those individually as we get going in this lecture. In this diagram here, you can notice that there's the substrate, which is commonly abbreviated S, and that's the ground state. We have a transition state, which is where the molecule, the substrate, is going to change into an intermediate, and you can see that that energy state is commonly the activation energy. To reach the transition state, we have to have the activation energy, and then after we overcome the transition state, we go to ground state. And the entire difference between the energy state from S to P is the delta G prime naught or delta G prime 0. Sometimes people call it delta G 0 prime, but all those things are common, the way to describe the difference in energy between the ground state of the substrate and the ground state of the product. So what does an enzyme do? An enzyme, and this is a reaction coordinate diagram that compares the enzyme in a catalyzed versus uncatalyzed reaction. In an uncatalyzed reaction, you have the black line where the transition state is really high and the energy, the delta G dagger, is very high. And with the transition state, you can see we have an enzyme. That's what the E stands for in the blue line. So we have a substrate, an E and S complex that's formed. That's the low energy state. That's a transition state that exists. And then we also have an enzyme product state that exists. And then we go to product. And you can see the delta G dagger between an uncatalyzed and catalyzed reaction is significantly lower in the case of the catalyzed or the enzymatically active reaction. And so these intermediates are very important in decreasing these enzyme substrate and enzyme product intermediates are very important in catalyzing the reaction and lowering the activation energy. Enzymes do not affect the equilibrium, very important to note. They only decrease the activation energy, which increases the velocity or the reaction rate of these products. So slow reactions face significant activation barriers or delta G daggers, and they have to overcome those in order for those reactions to proceed down to products. This reaction is the velocity, which is the V in this situation, is dependent on multiple things. And we can go over we'll probably go over the algebra in a different lecture, but basically there's a couple of important, this is the Michaelis-Menten equation. This is an equation you'll want to know and the variations of that. So we'll talk about what that means. So V is the velocity of the equation. So the velocity is dependent upon kcat, which is also referred to as the turnover number. And the turnover number is how many substrate molecules can one enzyme convert per second. So it's a numeric, has the numeric units that has per second. So that's kcat is equal to the turnover, also often referred to as the turnover number. The concentration of the enzyme is E, the concentration of the substrate is S. And then we have the Km, which is the Michaelis constant, and that's an approximate measure of an affinity, and a substrate's affinity for an enzyme. And so from there, we can calculate how fast a reaction goes. So in this slide, we can show, here are some of the things, how fast an enzyme can enhance the reaction. And I don't know if we can accurately assess how quick these things occur. A 10 to the 17th increase in reaction rate is incomprehensible to us, because that is, I mean, the order of reaction would be very significant. Even a 10 to the 5th increase in reaction rate is very, very fast, and it increases significantly. That we're talking about hundreds of thousands, if not millions or more reactions per second. And so it's a very, very substantial rate enhancement by some of these enzymes. How do we figure out what the kinetics of a molecule is? So it's pretty straightforward experiment. What you basically do is you mix enzyme and substrate, and you record the rate of disappearance for a substrate. So you do kind of have to have a substrate that's measurable. So something like a speck or some way of fluorescence when as it disappears. There's numerous ways of doing that, but basically you mix them, you test and see, and you're going to get a line. So you'll get a line that's shown here. In the example, they have 0.2 micromolar concentration amount, and you can see that they've measured the amount, and you get a nice visual representation of that value. Then you're going to do it again. You're going to do it with a higher substrate concentration, 0.5 micromolar, and then you do it again, and you measure again with 1 micromolar, and that'll give you the kinetics rate of the rate of reaction. And from there, you plot this, and then you can plug it into an equation, and you can figure out exactly how much you have. And this kind of gives you, on the left, shows you how you'd measure it. So you're going to have an amount, and as the amount decreases, you're going to plot the decrease as a concentration on a chart to determine the velocity. That's how we do it experimentally. That's how people, that's where you're going to get your turnover number. That's where you're going to get your Michaelis constant, your Km, and that's how you're going to determine all of those things inside an equation. So kinetics is all about velocity. It's all about reaction rate, and the reaction rate is very, very dependent upon the velocity. I've already shown you the equation, but one of the important concepts is the Km, so in this chart we have several important variables. We have Vmax, that's the maximum velocity that can occur at a concentration, and we cannot measure that experimentally. We actually we have to calculate it by doing the line fitting of this curve. So again, some of the other important things, Km is equal to half of Vmax. So if we can calculate Vmax, we can fit the curve, and then we can take half of Vmax, and that equals the Km. Actually, the Km is a concentration too. So it's the concentration at which half of Vmax occurs. So that kind of gives you an idea of how velocity is used to, number one, determine the equations for Michaelis-Menten, the Km for the equation, and it gives you an idea of how we actually calculate that in real life. Units are very, very important again. So Km is a concentration. Vmax is the number of units per unit time that we record. To put this back into perspective, so kinetics again is a velocity. How fast are we doing this? So mechanism of action are intricately tied with the kinetics. And so I like this chart because it kind of ties together the two concepts of mechanism of action and kinetics. So in the A part, we have no enzyme. You would have a transition state where, and this is a stickase, so it's a hypothetical example. I think it gives a good example for a relatable example of an enzyme. So assume the transition state is a bent stick, and the product is a broken stick, and you have a very, very high activation energy, and it's not going to occur just naturally. But an enzyme comes in, and it's complementary to the substrate, and it binds the substrate, although you're still going to get few products, because that activation energy, even though you have a nice decrease at the ES formation at the enzyme substrate complex, the activation energy is still very, very high. But if you take an enzyme with a complementary transition, it has a complementary transition state. So basically you can imagine a conformational change in that protein that allows it to break the stick. You can see that we decrease the total activation energy in the curve by a conformational change. So once it binds the stick, it conformationally changes. That can break the stick, and you can see that in the chart right there where the activation energy is decreased in the EP state, where the enzyme and the product are bound, and the transition state is stabilized, and then finally it goes to the product. And so none of the reaction rate is faster, but the delta G dagger has changed, but the delta G prime has not. So hopefully that gives you a good idea of how an enzyme and how enzyme kinetics is related to mechanism of action. Now, one thing you're going to want to understand is how all of these things relate. So again, Kcat is your affinity, or your turnover number, and that's related to how fast the enzyme works. And Km is your affinity, and that tells you how much a binding effect that they have. That's the Michaelis constant, and you can see the unit and understand the units. And I would understand this chart very thoroughly for your exam because it tells you exactly how. Well, it'll give you an idea of how effective an enzyme is and the relationship between the two. So and tell you how effective the enzyme would be. We can gain efficiency by having either high affinity, Km, or high velocity, Kcat. And these are both of them impact the overall velocity very much. One of the last concepts we'll talk about is the Lineweaver-Burke plot. It's a linearized double reciprocal plot, and it's good for visualizing visualize the Michaelis-Menten equation. It does have some problems, so we don't use. It's widely used just to visualize things, but it's not really used to calculate things. And so this is after you've already calculated all this. The slope of this line. So basically, you take an inverse of this plot of a normal plot that you see, and it's linear then all of a sudden, and that way you can kind of gauge where things are. So Vmax is at the intercept, the y intercept, negative Km is at the x-intercept, and the slope is equal to Km divided by the Vmax, and that gives you an idea. You can look at the plot and kind of get an idea, and we'll see this when we talk about inhibition. It provides great opportunity for us to just quickly visualize inhibition opportunities. So this is a kinetics measure that we will use later when we talk about inhibition. With that, we'll end on kinetics. The kinetics are, we don't do any examples necessarily here, but there's tons of examples in your textbook that I would definitely follow up with and understand the concepts. Look forward to chatting with you later about enzyme kinetics.